Afternoon, everyone. Thank you for attending our lab. My name is Ruan Vikramarachi. So I'm joined by my colleagues from the Institute, University of South Carolina, Dr. Angisha Alika, Revati Venkatramanan, and Dr. Amit Sheth, joining online, and as well as Dr. Lal Patel from IBM. The title of the lab is Developing Explainable Multimodal AI Models with hands-on lab on the life cycle of AI event prediction in manufacturing. First, let me walk you through the contents of the lab. First, we'll provide an introduction to what is AI events, why is it important, and the challenges associated with the AI event prediction. The first hands-on session will be on exploring the datasets, the real-world datasets that are available for AI event prediction. Then the second session will focus on addressing the data scarcity and improving the quality. The third one will be on anomaly detection and Industry 4.2 applications and the enterprise applications. The final session will be on the development and the use of ontologies in the AI event prediction. If you have any questions, yeah, we'll be happy to answer. So let's briefly look at what are the objectives of this lab. First, we want to understand what is AI event prediction. So what are the challenges associated with it? Why is it actually important in the real world industrial, Industry 4.2 domain that we work on this important problem? Then second, we want to look at what are the data sets that we can use, both analog and multimodal data sets. Researchers can use to develop models for AI event prediction. Third, we want to look at what are the benefits of combining more than one modality. Standard, time series forecasting algorithms may only look at, sensor data, numerical values. So, is there any benefit in integrating more than one modality for the AI event prediction? Fourth, we also want to look at so how can we improve the explainability of these models by developing process ontologies and integrating them with the prediction models? Since this is a lab, we also want the participant to actually run these, the models, load the data sets, explore, and provide a collaborative learning and networking environment. Finally, we will also look at what are the advanced machine learning techniques and the theoretical the machine learning aspects that we can use for AI event prediction. So first of all, the AI events are defined as infrequent events that are defined by the specific spatial, temporal, and the semantic context. So the examples include the equipment failures in manufacturing cells, quality defects, and supply chain inventory issues. So while these events are extremely rare, the repercussions of these kind of events are actually big, because, for example, the prior research indicates that these rare events would cause financial losses of approximately $20,000 per minute and 50 billion annually. So it highlights the importance of investigating and conducting research in this domain. And we also want to look at the importance of modeling and the machine learning models that we can use and the technical challenges associated with it. So, for example, if you want to use, let's say, a standard machine learning or classification algorithm for AI event domain, then we face the issues, for example, with biases, because we have extreme data imbalance. So in that case, what are the special techniques that we can use, both in terms of preparing your data, handling your data, as well as developing models. And overall, we would look at what is the overall impact on this kind of AI event prediction models on operations and improving the quality and also mitigating the failures. So throughout this lab, we'll be using a couple of Google Colab files, and all the data sets, slides, and the Colab files that we would use are published online. So please scan the QR codes that are displayed now. The GitHub repository will have the slides as well as the links to the collabs. You can get all the data sets that we are discussing or using today from the second link, and slides that we are using from the third link. Next, I will walk you through a quick overview of the subsequent hands-on sessions. So the first one, which is conducted by me, I'll walk you through exploring the data sets for AI event analysis. We look at publicly available AI event data set as well as one that is generated from one of our collaborators at the University of South Carolina. Second, Chaturanki would look at addressing data scarcity and improving the quality, so the data augmentation, cleaning, and all those kind of methods. She would walk you through with a couple of Google Colab files. Third, we would have Tawal walking you through the anomaly detection in Industry 4.0 and industry enterprise applications. Fourth, Revati would lead the discussion on the development and the use of process ontology for event prediction. Yeah. Before I start the first hands-on session on exploring data, is there any question? Are you able to access the data and the collab files? Yeah, if not, please raise your hand. Our team will help. Yeah. Okay, let us start the first hands-on session. As I briefly mentioned about the modalities, so most of the data sets that are out there for anomaly detection and the event prediction, they are numerical. But in this particular tutorial, we look at actually two data sets. One is a numerical data set, the other one is a multimodal data set. So we have, that's why we have a mix of data sets with different modalities. And the second point I want to highlight here is that when we looked up the literature on the AI event prediction, we could not find the clear classification of the AI events. So in our prior work, we have introduced this concept of levels of rarity. So we have categorized the rarity levels into four main groups. R1, which is extremely rare case, when the data set naturally exhibits less than 1% rarity, we call them extremely rare, or denoted as R1. And the R4 category is the frequently rare one. So those have more than 10% rarity percentage. So if you are familiar with anomaly detection kind of data sets, those data sets have more than 10% rarity usually. But the ones that we are actually showing here, the publicly available AI event data sets, you can see the rarity percentage is like, for example, the pulp and paper manufacturing data set that has the rarity percentage of 0.67, which I'll actually have a hands-on session on. The second one is the air pressure system ATS failure data set, which is 1.767 rarity. And Bosch production line data set is 0.58 rarity, and the future factories data set, which we'll use, has 1.7%. So these data sets can be used to study a couple of mainstream tasks. So the first one is the AI event detection and prediction. The second one is the anomaly detection and prediction. The third one, although we are not covering it in this tutorial, is the long-term and short-term forecasting. So in this tutorial, we, given the limited time that we have, we are only considering the AI event detection and prediction as well as the anomaly detection and prediction. So when you look at these data sets for AI event prediction, we observe several common characteristics. The first one is, and the challenges also. So they have a highly skewed class distribution. And when you try to collect data from, let's say, pulp and paper manufacturing plant, it is a challenging task to retrieve a high quality data set with the naturally occurring rare events, because as the name suggests, these events don't occur that often. So it's a challenging task. And when you have a high quality data set, you would observe that the data distribution is extremely scaled. And the second, the natural property that you would observe with the rare event data set is they have the temporal associations. The data points are temporally associated. So if you're someone who works on actually anomaly detection, you may find data sets that are actually not temporal. So, but in one thing I want to highlight is in the rare event prediction data sets, almost all the data that you find are temporal data sets. Third, these events are actually extremely rare. There's a high class overlap. I mean, if you look at the variables that contribute to, let's say, a particular event, you would have a high overlap between the common class as well as the rare event class. And when you ultimately generate models, develop models and then deploy them in real-world environments, so uncertainty is also a challenging problem because of these naturally rare and extremely skewed data distributions. There's a natural uncertainty associated with the models. The fifth point that we want to highlight is when you have, let's say, more than one modality, and then we want to, let's say, fuse both the sensor data as well as the image data, textual data, then when we develop models, we will also face the high dimensionality issue because fusing data from multiple modalities that will naturally cause the high dimensional issues. And finally, we have also come across situations where the events themselves are complex because there are some simple events are also complex events. So by complex events, what I mean is these events get triggered as a result of more than one event occurring at the same time. So the contributions to a particular high complex event would not just triggered by one sudden, let's say, change in one variable. So these are the associated challenges as well as the characteristics of rare event datasets. Then it begs the question, what are the factors that cause rarity, natural rarity in the dataset? One is a natural occurrence. So let's say we have I'm taking the same example that we'll use, the pulp and paper. So when you develop a manufacturing cell, you would think of all possible scenarios that this plant can fail, right? So you would try to mitigate those failures beforehand. So because of that reason, when an actual error occurs, that is a naturally rare event because you would anticipate all the other failures that you can think of when you actually deploy the system, because failure due to these kind of events would cost a huge amount of money. And rarity can cause in data sets because of the measurement issues. If there's an issue in the incorrect measurement of a particular variable, then that could also lead to a rarity in the data set. Also, sampling bias is a reason that sometimes you may have a rarity in a data set. Also, the class definition, what I mean by class definition is, let's say, when we decide to create a data set and collect data from a actual manufacturing cell, we may try to either think of a granular class distribution or fine-grained or coarse-grained class distribution. So if we are going with, let's say, a fine-grained, that means we have lots of classes that we want to define, then one or two particular classes could actually have a natural rarity there. Also, the subjective decisions that like the class definitions can cause rarity in a particular data set. So next, I will give a brief introduction to the two datasets that we will be using throughout this lab. The first one is the pulp and paper manufacturing dataset. This dataset was released by a company called Process Miner. This is a naturally rare dataset with natural rare events. So the manufacturing environment is you have the pulp. So you have the entire process from creating papers, different types of papers from the pulp, actual paper pulp. So in this, we have, I think, 28 different types of papers. The dataset that they have released contain about little over 18,000 records collected over 30 days. Sampling frequency is 0.5 hertz. And we have 61 variables collected from different sensors. The predictive variable is just a binary whether there's a paper break or not. The rare event here is whether there's a paper break. So did we have to actually stop the manufacturing process due to a paper break? That's the rare event. In this case, we have 0.67 natural rarity. So this would fall into the R1 category in our taxonomy. A second data set, which was released by one of our collaborators in the University of South Carolina, the McNair Aerospace Center. So I will actually give more details in the coming slides. So we have a robot assembly setup. In this particular data set, they have like physical sensors on the robo arms as well as the conveyor belt. And they also have mounted cameras looking over the manufacturing set. So there are two versions of the dataset that's been released. The first one is analog dataset, which contains only the sensor variables. The second one is the multimodal one, which contains both the image data as well as sensor variables. There are different types of sensors that are mounted both on the robos as well as the conveyor belt, like the potentiometer, the load cell, the conveyor sensors, robot angles, the drive temperature. So when they generated these things, is a real world data set, they actually faced this issue. You have to synchronize the data that are generated from the sensors as well as the cameras. So the second version that they have released with the multimodal data, they actually made the synchronization intact. So you would have the image data from the same timestamp a particular sensor variable is collected. So there are 285 assembly cycles, 21 distinct states. I'll explain what those distinct states are. And we have different 7 actually anomaly types. So the anomalies are actually predefined in this case because this is sort of a controlled environment. So since this is a like robot assembly, there are different components that make up the whole robot, right? So when the nose is not present, we have the no nose. When, let's say, the body part 2 is missing, we have the no body part 2. So likewise, they have defined 7 different types of anomalies. When talking about the rarity, in the analog data set, the rarity level is 1.7%. In the multimodal data set, the rarity percentage is 45.3, which means the multimodal data set actually can be used to study anomaly detection as well, because it has a high rarity percentage. So this is the actual cell. What you have on the right is like bird's eye view of the manufacturing cell. So you can see that there's a conveyor belt, which is in black. So that's where the parts are being actually transported to different robo arms. So there are 21 states being defined here. So if, for example, the state 4 is body part 1 is assembled. State 6 is body part 2 is assembled. So likewise, from the start point, it will go through the cycle of assembling the rocket, and then it will also go through the cycle of disassembling the rocket. So in different timestamps, they have introduced these rarity events, like rare events. particular part is not present, particular part is, incorrectly, assembled. So when the data set that we have shared earlier, you can actually look up the image data as well as the sensor data in the CSV file. So next, I'll move on to the lab sessions, exploring these two data sets. Before I move on to the lab, are there any questions from the introductory part? Okay. You open up the first part. So the links actually here as well. You would have access to all these Google Colab files. So let me first actually show you the data set. So this is the multimodal data set. So let's say we selected cycle state 9, and then let's say we pick the rearrangement of no nodes. That means that the node is not present. You can find all the images here, and so each image has a bounding box, right? Let's say that this part is now labeled. So the bounding box that you see in red, all the coordinates for bounding boxes are actually in the detections.csv file. So if you open up this Google Drive folder, you'll be able to navigate to each event type, and you can find the image data as well as the sensor data and the detections, object detection bounding boxes as well, coordinates for bounding boxes. So the first lab session, I'll be exploring the pulp and paper data set. So let's first load up the relevant, necessary libraries. So we'll be using standard like pandas, NumPy, matplotlib, sklearn, and seaborn. So this is the CSV file that we have for the pulp and paper manufacturing dataset, the process miner AI events mts-data.csv. When you load it up as a pandas data frame, you can see that this is timestamp, and the Y variable basically shows whether there's a paper break. If there's no paper break, it's 0. If there's paper break, that will be 1. It's a binary variable. And we have 60 variables, sensor variables, from sensor readings. Let's look up the data, brief, data set statistics. So you can see in most of the cases, we would have floating points because this is the analog data set. So we don't have any image data here. We have about a little over 18,000 data points with 60 variables. And next we would just look up the ranges for each variable. You can see it ranges from in some cases like negative, some cases positive. For example, this one has like a huge range. There are some null fields as well. This cell is all about briefly, printing just the mean, standard deviation, min max, basically the ranges of each variable. So this is actually interesting. The next part, which is visualizing the class distribution. So as I told, it's less than 1%. This falls under R1 rarity category. You can see from the Y distribution of the Y variable, which is the target variable, the disparity between the normal and the rare, naturally rare events. Next, we would look up the heat map that is showing the correlation between the variables. So actually, in this case, we have plotted like all 60 variables against each other and see whether we can see a correlation. So why this plot is interesting? So this actually shows the challenge inherited in rare event data. You would not see a clear correlation among variables. If there's a clear correlation among variables, then we would have actually isolated these variables and then use those to identify rare events. But in this case, what this shows is in a naturally rare occurring data set, rare event occurring data set, it is extremely hard to spot these events by just looking at the distributions of each distributions and the ranges of each variable. Yeah, the next cell actually further confirms it because in this case we are trying to plot the time series trend of 3 variables. You can see that so these 3 variables don't follow uniform trend that we can actually handpick and then further study. Yeah, in the next case, we also wanted to look up whether there are outliers that we can actually spot. So in this box plot, you can see with respect to some variables, there are some outliers, but we are showing just 8 variables. So up until this point, what we have done basically was to confirm a couple of things. So we wanted to just load up the data set as a pandas data frame, and then do some exploratory analysis to see, to confirm that this actually a naturally rare event data set, and it is not an easy or trivial task to try to build a model to do rare event prediction. So in the second notebook, we'll do pretty much the same with respect to the future factories dataset that has a multimodal content. If you actually copy the Google Drive folder, like multimodal dataset, you can find this FF yeah, this is the FF multimodal.csv file. So I wanted to give you, show you something here. Let me just. It's taking some time. By, oh yeah, okay. So since this is a multimodal data set, so you would have a few more fields in this particular data set. So the cam1 and cam2 are the 2 cameras mounted looking over the manufacturer itself, right? So you can find the path in the folder that is relevant to this particular timestamp. So camera one would have a link that you can use, a relative link that you can use to actually access the image data. This one, we would look at first the different values, different states. So as I mentioned earlier, this has over 40% like rarity percentage. So this is not a like extremely rare case, the multimodal data set. So we have about 90,000 normal occurrences, but then these are actually the different types of events that they have defined in the data set. For example, there are 1,078 data points with missing body part 2. Then no-nos, 19,307. We can also do the same thing that we did in the previous lab to look up what type of, what is the data type? Are there any null variables? And also to look up the missing values and the summary states, variable summary. Since this is pretty similar to the previous one, I actually, let me move to the, this part. This is pretty interesting. So in this one, actually, we looked up like each column. See this first, we will first look up the first 3 numerical columns. So we are trying to find out the distribution. So you can see they have, so if you look at the VF, QVFD1, this is temperature, and QVFD2. So they have actually different distributions. So because this data set is actually pretty different from the pulp and paper because this is developed in a control environment. So we actually knew exactly when an event occurred. Even in that case, when you look up the distribution, this actually pretty different. And then we also did the sort of data analysis on the categorical variables. We can see the cycle state, the actual state, and the cycle count here. Also, the correlation metrics that we did in the previous one as well. So here you can find the different states, different variables, and then see whether there's any correlation, any known correlation. So even in this controlled setting, controlled data set, you cannot actually see a visible correlation. So that's also actually showing even in the anomaly detection data sets, it is not easy to develop models by just looking at the correlation statistics. I think we already looked up these brief statistics. So before I hand it over to Chaturangi on the development of, like the data augmentation and the data quality improvement, are there any questions on loading the data sets or accessing data sets? Yeah, please feel free to raise your hand and let us know. So if there are any issues, we are happy to help. Because in the next couple of collab labs, we would actually look up, we would actually load these data sets and then, develop, walk you through the development of models. I think in the interest of time, I'll wrap up. Chaturangi would take over from the second lab, which is on addressing the data scarcity and improving the quality.
Thank you, Rohan. Good evening, everyone. I am Chaturangi Shalika, a PhD candidate at AI Institute, University of South Carolina. So in this session, I will be working through on how to address the data scarcity prevalent in rare event datasets and how we can improve the quality of a dataset in order to make better predictions from the machine learning models. So what is data augmentation? So Data augmentation is an effective way to enhance the size and the quality of training data that we can use for any machine learning pipeline. So augmentation has been used very much in the computer vision and image processing domain. So it's kind of a new and like obsolete technique that has been used in time series analysis. So in this session, I will be explaining how we can use data augmentation techniques, especially in the sense data, which means the time series data that we have used. So as I explained earlier, data augmentation is a process of artificially increasing the amount of data points by generating new data points from the already existing data. And in this process, we do minor alterations to the data using any learning algorithms that we have in our hands. So this is a popular taxonomy of time series data augmentation. So this taxonomy we got from the survey paper on time series data augmentation techniques. So as you can see, the time series data augmentation techniques can be divided into two major techniques as basic approaches and advanced approaches. So in this session, I will be explaining on how to use both of these techniques for our event dataset. So for example, uh, the basic approaches include like simple techniques like cropping, flipping, and jittering, or adding noise, or reversing a uh, uh, time series dataset. So they can be categorized into three main techniques as time domain, frequency domain, or time frequency domain. Means in time domain, we make the change to the time component in the time series data. And in frequency domain, we do the change to the frequency of the particular time series. And in time frequency domain, we alter both the time and the frequency domain of the particular time series. And for the advanced approaches, there are three major types as decomposition methods, generative models, and learning models. So yeah, so in this session, I'll be holding this hands-on session on how we can use each of these basic augmentation methods and advanced methods also in the time series analysis. So for this session, I'll be using this particular notebook. So you can scan this QR code to access this notebook, or else you can type this short URL in order to access this notebook. So if anyone has any problem in accessing this notebook, let us know. So in the previous session, Ruan explained how we can load a particular data set and how we can, yeah.
Could you show the board again?
Sure. Yes, so in the previous session, Ruan explained how to load the relevant data sets and how to view the statistics of that. So in this session, I will be using the future factors multimodal dataset in which he introduced and explain you how we can incorporate this data augmentation technique in order to achieve better prediction. So the first steps the same as this section. So we import Miniscid libraries and then we load the future factories multimodal data sets. And then so there are a couple of data exploration techniques that I have included here, like finding uh, the anomaly types and their respective counts, same as which was included in his notebook also. And then so we are doing like mapping the categorical values into numerical values in our datasets, and again finding the respective counts for each of the numerical anomaly labels that we have. So moving on to the main part of this section, the time series data augmentation. So for the basic data augmentation technique, we use this particular library called a TS augmentation, which is an open source Python package for time series augmentation based on time series data. So this TS offers a set of augmentation methods specific for time series, as well as it includes a simple API that we can use to combine a different basic time series augmentation methods into a single pipeline. So to install this TSO, you can simply install it through a pip install method, and alternatively, you can install TSO from the source code itself, but the problem with that is it will give you the latest, but it is unstable version of TSO. In this TSO Python package, it offers 15 different augmentation methods. So for example, they include techniques like cropping a series, magnifying and flipping means reversing the timeline of the series, and also adding noise. And also they offer some other methods that are specifically designed for time series data, like time wrapping, side tracking, or superposing like things. So to give some understanding and introduction of what is happening in this basic augmentation techniques. So these are some of the techniques that I'll be using in this lab, like adding relatively change the time series of a series and using time series lag features. Like so in lag features, what is happening is we believe that the future time series are based on the past time series values. So we kind of match the patterns and import it into the time series augmentation. And also techniques like rolling window, expanding window, and we can use techniques like 1D convolution of time series into the existing series. And also there are techniques like pooling, drifting, reversing a series, adding random noise, time wrapping, and quantization techniques. So these are all some interesting time series augmentation techniques that we can use to improve the quality of our dataset. So to incorporate these techniques, to visualize first, we can import this TS of visualization technique. And then, so in this plot, I have visualized one variable of our multimodal time series dataset, which is the RO2 gripper potentiometer value, means the potentiometer value respected to the robot 2 in our dataset. So you can see the variation and the minimum and the maximum values of this particular sensor variable here. And you can see how it is fluctuating. So, so this is an anomalous dataset. So while we are just referring into the sensor variations, we can't focus what is the anomalous records and what are the non-anomalous records. So it's pretty difficult to identify and predict these anomalies in advance. So as Ruan explained, this is kind of a hectic thing in manufacturing domain. So let's see how we can combine different time series augmentation techniques into one single pipeline. So this TS library offers a simple API that we can use. We can combine these separate techniques together. So this is the method that we have used. And also, so this my augmenter is the variable that we have used to combine these separate time series augmentation techniques, where I have used time wrapping, cropping, quantizing, drifting, and reversing a series. So this is the output of the augmented time series that we have received. So here the blue line is the usual time series that we have, and from the red red vertical lines, we can see the difference in the time series that we have from the augmented series and also the original series. And then we can get the summary of the particular data augmenter that we have developed. And so that is the way that we can use basic augmentation techniques, and then moving into the advanced data augmentation techniques. So here I will be explaining how to use a seasonal trend decomposition technique as the advanced data augmentation technique that we can use in time series analysis. So you may, some of you may know what is happening in this seasonal trend decomposition technique. So in this technique, we decompose a particular time series into its into its three components named trend, seasonality, and residual. So trend means the long-term patterns that exist in a dataset. So it can be either increasing or decreasing order. The seasonality means the repetitive patterns and fluctuations that can be seen in a time series. So patterns like we can see some patterns like weekly occurring, monthly or yearly in a particular time series. For example, we can say that the sales of a particular company will increase in this particular month or in this particular day, likewise. The residual means the random and irregular fluctuations and noise that occur in a particular time series. So when we are doing time series analysis or anomaly detection, we usually try to remove this noise if we can do so in the time series in order to get better predictions from our models. When we are using this seasonal trend decomposition technique, in the algorithm, in the particular algorithms that they have used to model this seasonal trend decomposition, they have used two modes. That means we can think that seasonality, trend, and the residual can be added together, or else they can be multiplied also. So depending on the type of data set and the use case that we have to select the best mode that we can use in order to combine these three components. So how to choose between these additive and multiplicative decomposition? So it is said that the additive model is useful when the seasonal variations of the time series is relatively constant over time. And also we can use the multiplicative model when the seasonal variation increases over time. So in order to demonstrate how we can use this seasonal trend decomposition, we use TS stat models.tsa. This particular library is a scikit-learn package. So we can retrieve the trend, seasonality, and the residual components like this from using these stat models. So here you can see we can get the particular model and the period of a dataset. So what is this period that is included here? This period is the repeating cycle in this dataset, or else we can say it is like the samples that the number of samples that that are responsible for one particular cycle of the series. So in this particular future factors multimodal dataset, if you have seen noted into one slide, it's included that the frequency of the series is between 1.8 to 2.2. So means the future factors multimodal dataset frequency is not uniform. So that is a common observation that we can see in manufacturing related datasets where the frequency of the datasets are not uniform. So this can occur due to several reasons, like the errors in the machines that they use to collect the sensor data, or else the measurements, the statistics of the machines, like things like that. And also the environment conditions also affect the difference in the frequency that we can see in the real world manufacturing data. So from this code, we can apply set models to get the trend, sequence, and the residual component existing in time series. And then, we can display the transform dataset like this. So as I mentioned earlier, the frequency of the real world time series dataset may vary. So how do we find the period of dataset very accurately? So there are different methods, statistical methods that we can use to detect this period of a dataset. So I'll explain you two methods that we can use. So in this particular future factories multimodal dataset, uh, the we can see that uh, the sampling rate or the frequency of this series is around 1.9. So here I took the mean of the frequency which range from 1.8 to 2.2. So we can see the period is uh, and also this in this future factors dataset, the approximate time taken for one cycle is 5 minutes, means 300 seconds. So we can get the period from this dataset, multiplying the approximate time into the frequency, means it is closer to 585 observations, means approximately 600 rows represent one cycle in this particular dataset. Uh, so if we take the cycle, the one cycle as 600 observations, then we can take the period as 600 and then get the augmented series as this. So it is pretty straightforward. And also there are other statistical methods that we can use to get this period in a mathematical way. So I will explain two techniques that we can use. The first technique is using autocorrelation plot. So this is the way that we can use this autocorrelation function in order to detect the periodicity of a dataset. So in this code snippet, I have used the ACF function to 2000 timestamps and see if we can detect the periodicity of this dataset. So as you can see, there is no regular pattern that we can see in this dataset. So we can conclude that the ACF method or the autocorrelation function is not suitable for detecting periodicity in the future factory multimodal dataset. So for the datasets like this, we can use another method like fast Fourier transform in order to detect the periodicity of a dataset. So in this code snippet, I have included how you can use fast Fourier method in order to detect the periodicity. So there are some steps that we have to follow, like we have to remove the mean from the particular series in order to get follow the steps, and then we have to apply a high pass filter to remove the low frequency strings. So this step will help us to preserve only the high frequency variations which are dominant in our dataset. And then we can perform the fast Fourier transform technique. So what happens in this fast Fourier techniques is it converts the time domain signal into a frequency domain, which will help us to identify the patterns in our dataset. And also then this fast Fourier method will result in both positive and negative records. So for our analysis, we only keep the positive frequencies for the detecting the periods of our dataset. And so this is the results that we got. So this x-axis represents the magnitude of the frequencies, and the y-axis denotes the frequency. So as you can see around here, like in the when the frequency is around 0.0135, we can see some high peaks here. So we can decide that this is the periodicity of our dataset. Means we can detect the period once in 74 samples in our dataset. So yeah, from using this method, we can detect how we can apply particular time series augmentation techniques for our particular data set. So uh, yeah, so how we can select the best augmentation technique for our scenario and the kind of data sets we have in our hand. So here we have identified 5 techniques that we can use to select the best augmentation techniques for our use case. So we have to consider the data characteristics that we have, and also we have to address the sparsity and the skewness of our data set. So Ruan explained how the data scarcity is an issue for rare event analysis, and the rare event data sets are skewed. So we have to address that issues also, and also we have to handle the noise and the variability of the time series, and also the multimodal data sets that we have in our hands. And also uh, there are some other techniques where uh, other challenges that we have, like we have to deal with the temporal patterns in our time series datasets. So we have to make sure that the kind of data augmentation techniques that we use will not destroy the temporal patterns and the statistical patterns in our time series datasets. And overall, we have to find the way to balance the complexity of the relevance datasets, and also we have to make sure that we are not exceeding the computational cost while using these data augmentation techniques. Yeah, that is the session and my part. So the next session will be done by Dr. Dawal from IBM, and he will be explaining how we can use anomaly detection techniques, especially in Industry 4.0 applications and enterprise learning. Thank you.
We'll switch later. This one is fine. Okay. So I will start my session. And things that we are going to cover in today's session is we have seen, our life has completely changed with large language model, right? And everything is going to change. Even how we are going to build our anomaly models, right? So I'm going to walk through a couple of examples, right? Like how we used to build the anomaly models in a traditional way, and how we kind of, there is an emerging way, right? So let's start with. So these are the 4 topics I'm going to cover in my 15-minute presentation. We'll start with the traditional way of, building an anomaly model, which I think the Wuhan and, the team has already covered in a greater detail. And then I will walk through, the new evolution that are happening in, this emerging field. So I have 3 examples, and where it will help you to do acceleration work, right? So let me start with, the traditional way of building the anomaly model. And means anomaly detection model is not like a new thing that we are building in these years. It has been there for a long years. And there are a lot of challenges that we have encountered, right? And one of the bigger challenges is that every time when you wanted to build any anomaly detection models, you have dependency on your subject matter expert, right? Like, and subject matter experts are always kind of, available, not available, like, and they are expert in certain field, and you wanted to build the model. So I think some of the gap that we identified when you really wanted to do machine learning or any deep learning work, right? The first thing is that you need a domain expert who help you, right? What is the problem that you wanted to solve? And the second things like, so we highlighted like 2 key challenges, right? Like, it's in general applicable to kind of any machine learning algorithm. So, and it's like we come from the industry, so we will always recommend, the strategy that you should follow, right? So I think CRISP is like very old methodology that we actually recommended to follow. right? That, how do you solve your data mining or machine learning problem, right? So you start with business understanding of your problem, that what is exactly the problem I'm trying to solve, right? Once you understand your business problems, you go to the next step. Okay, I will try to understand the data now, right? Like, what is the data that I should use to actually solve my problem, right? And many of you have already experienced this kind of, it's like a common problem, right? Like, and this is where, and then it's actually a cycle, right? Like, just like a software engineering, we have waterfall models and different, cycles to follow. This is basically the cycle that we follow in a data mining kind of projects, right? That we did, we exactly highlighted in the previous two, like, you need to prepare the data, then you need to model the data, right? And then you go for the evaluation. So the previous two presenter already discussed this flow, right, on the left side. But what we are offering now, right, like where we are going, right? So I think we are saying is that something we can automate, right? Something we can automate with using LLM. So what we are trying to automate here, right? So you have already seen, right, like what LLM can do. LLM actually can do a lot of good role play, right? They can actually play a role of data scientist. They can actually play a role of subject matter expert. And that is what I'm going to show you in next kind of couple of slides, right? Like, so you can see, right, like you can create in a simulated environment where you are basically using LLM, but in a different context, right? So, you can create a reliability engineers who will, and you say that reliability engineers are expected to have a knowledge about the industrial domain, right? I mean, the LLMs are already being trained on a large corpus of data. So you can assume that they might have read the books and materials, wikis and all, so they know it. It's just a matter of, how do you kind of create them? So what you see on the right side is our focus, right? Saying is that I can use LLM as a base foundation. And then on the top of these LLM, I can actually create a lot of virtual agent, right? Persona, what we call it, right? And then enable them to communicate with each other. Saying is that you talk to each other, then help me to solve the problem, right? So you bring a collaboration layer on the top of it, right? And then you solve your business problem, which is what I actually highlighted on the left side, right? Like saying is that you really need to do collaboration in order to solve the problem, right? And that's what we are kind of, recommending. So we have a one papers in the workshop toward the end, where we are going to discuss, this idea of like, multi-agent systems talking to each other, solving certain problems. But you are going to get a glimpse today. So again, right, complex, right? Complexity is always part of our life, right? But we are trying to simplify it. So this is a traditional way of like, building anomaly models. You will have to identify feature columns, methods, univariate, multivariate, supervised, semi-supervised, right? I mean, this literature is already there, and I think we are trying to actually automate it. So start with the first application, role-playing LLM. So here you will see that, we have LLM and we are creating a role. And that's what I think we kind of standardize, right? That you can, like it's just like a script writing, right? Like, so you can create an agent, say, okay, your name is ABC, you have this skills, your skill is like, you are expert in reliability engineering, and you have some asset like chillers, and you will help us to kind of provide all the domain knowledge. And the remaining, parameters are all the LLM specific, right? I will use, IBM Granite models to actually build the agent. So in the middle part, what you see, right? Like I created a facilitator, like normally whenever you have a meeting, you will always like a manager to actually facilitate the meeting communication, correct? On the top of it, I bring SME, reliability engineers, quality engineers, but these are all the role-playing agents. So everybody is kind of, given us very specific instructions. What is your roles? What are you going to do? How are you going to communicate with each other? But this is basically the future, right? And, we enable some communication between them, that you are free to talk to each other, right? And then, but the purpose of talk is very precise, right? What exactly we wanted to achieve as a goal, right? So I wanted to build an anomaly detection model, and you can use all these, persona to help you to identify what are the important sensor variable I should be utilizing. Very simple, right? And they will do it, the job, right? So this is basically like, two examples that we identified in Industry 4.0, right? So one of the example is like a failure mode and effect analysis, right? Typically like, if you have any asset, industrial asset or any other asset, right? You need to know what are the different failures that your machine encounter. That is basically the left side, right? You need to know what are the different failures that can happen, right? The right side is okay, so now I know what are the failures that can happen. I am going to instrument certain sensor on the top of those, machine, right? So the right side is actually talking more about that. I mean, I need to kind of revise the slide, but the right side is more about, you know, how I will create a kind of, multi-persona things, and they can talk to each other and help me. So in the next slide, I will show you, right? So this was basically, I created a persona. I give them a very nice instruction that you are going to act as a reliability engineer. On the left side, I say, okay, you're going to act as a subject matter expert. And then in a natural language, I describe what they need to do. So if you see, right, if you read it very carefully, right, everything is a natural language. Right? Understanding of LLMs are kind of, has enriched. And I think, just by specifying, the agents, right, and the roles, and then building a framework around it is sufficient enough for us to actually solve the problem. So this was one example I wanted to start. This is another example, say, okay, why don't I have a data scientist who actually help me to write a code, right? And the data scientist will talk to the subject matter expert, say that I wanted to build the anomaly detection models. My job is to identify important sensor variables. And then the subject matter expert will help you to actually identify, for a given domain, what are the important sensor variables that you should be monitoring. So I think what I'm trying to give you like a glimpse is that the things has been moving much faster rate. The way we used to build the models, now we are actually bringing LLM as a part of our day-to-day, right? Right. And I think these were the two examples I thought I should share it with you. So now I will go to the second, so in a previous examples, I already kind of, indirectly mentioned you that all this role playing happened because LLM has understanding of certain domain. So now if LLM has an understanding of certain domain, I can actually even extract that knowledge out and put it in a form of the ontology, right? Which I think the last presenter is going to cover it. So I'm going to give you a glimpse of this, right? So the top part, what you see is the knowledge, right? In some structured form, but we are actually taking out from the LLM. So now I'm not going anywhere else. I'm going to LLM and say, okay, I have a one industrial asset like standby generator, right? Hospitals actually use standby generator a lot. Why? Because if the power supplies goes down, they need to actually bring the power back, the guarantee, right? So standby generator is a very important, like asset, data centers, right? They use it, right? Hospitals, they use it. So what we did is that, oh, I'm a data scientist. I need to build an anomaly detection model for this asset. I don't have SME, right? But I need a knowledge. So from where the knowledge will come, right? So you can see that I started kind of, building this knowledge, whatever we say, right? Like it's an ontology, graph, whatever we say, but it's fairly structured way, right? So I say, okay, standby generator is an asset. It can have multiple components like engine, alternate, batteries, right? And each of the component actually can encounter a different failure. So for example, engine can actually have overheating. Now, if I wanted to detect the overheating, I would actually put certain, sensor on the top of it, which is what the last, like, the two rows, right? Like pressures, flow rate. So these are the sensors or some kind of, KPI that I should monitor. And then the last row is like the behavior that you need to monitor, right? Like, is it going to increase? Is it going to reduce? It is going to like what type of like, abnormality you will see. So you can see, right? This is just an example, give an example like this becomes a document for you to actually build an anomaly model, right? Because when you wanted to start building an anomaly models, you need to know what exactly anomaly, what sensor variable I should focus, what should be the signature of my, time series and all. So the point, the message that I'm trying to give you is things are in front of us, right? Leverage LLM as much as you can, right? More problems I think, will be overcome, right? By the researcher. There is a large team who are working on factuality, right? So they will help you that, if you uncover. So I think these were the second things, right? Saying is that LLM has a knowledge. It's just a matter for you to actually, probe it, navigate it, and then get the information the way you want. And then once you have that information, the life become very easy. Then you can actually bring your real data set from the operational environment and then match it, right? That, okay, do I have sufficient data or not? So just compare the previous two presentations that we were talking more about. I have a data and I'm now working on it. Now we are giving you a complete prescription that, you can start with even this prescription and go to the data and say, okay, which data I should be kind of fetching out. So this is the second example. Again, I say that there is a workshop papers we have just to discuss on this particular topic. So maybe like, this is also like going deeper of like, how we are using LLMs to actually do the anomaly modeling, right? Not only the LLM, but, right? Okay, so I give you two examples, right? Now, the third example is the agent, which is, the third kind of, wave is after the LLM. The third, it's like next thing is the agent, right? So now I'm going to give an example of the agent, right? So far I introduced that LLM can work as a data scientist, good. And then I give you the LLM also have a good knowledge about the industrial asset. Good. Now what I can do on top of these two things. So the third thing is the agent. You can build the agents to do the automation work, right? So give you the problems, right? Life is not as simple as we think. This is the complex industrial asset. It's a chiller. And it will have like so many components that can fail, right? So many anomaly models we used to build on, this industrial asset. And I mean to say, for example, data is always an issue, failure mode is an issue, right? So there are plenty of challenges, problems that we always encounter. And now here is what we are saying is that, instead of having a lot of manual, can we actually do some automations with using agents and then put the agents here and they can help us to build the anomaly detection model. So this is basically, it's like, some thing, because, this is the first time probably you might be kind of, hearing, right? That, okay, so what exactly the agent? Is it just a software program? Or what is the prescribed, that like a textbook definition, right? What is the textbook definition of the agent? So this slide gives you a kind of, I would say, glimpse of like, when I say agent, what does it mean? Agent is not just an LLM, by the way. So agents are like almost a piece of the things which should able to do three important things. Like they should able to do think. That's what you can see, right? The hard part, right? They should able to think in autonomous manner. Okay. Once you think, they should able to act, and then you should observe, right? So it's like a human psychology, right? That you should able to think, then you should act, and then you observe your act. And if you are making mistake, you actually recover from your mistake. And that's what the definition of the agent, right? So this particular, slide may be very tough to kind of, capture in like a short amount of time, but you see like the agents actually interact with environment. They go somewhere, download the data, and then open the data and see that, oh, something is not right, right? So basically agents they should able to think, act, observe, and then go back to the environment, come back the information, and then go to the next step. So what I'm going to do now is just, I give you a demo, right? Like I just prepared for the demo. So what I'm going to do is now I'm going to switch over, to my machine for a brief period of time. So I'm going to share my screen. Give me like 2 minutes. You need to off the host. Host need to turn it off. Okay, so yeah, good. Okay, so I'm going to do the same things. I'm going to build the anomaly detection model with using sensor data, but I'm the operator. So I am the operator means I'm the consumer of the system. So being a consumer of the systems, I came today and say, okay, one of my asset, which is chiller 11, it's like an asset, industrial asset I was showing in the previous slide. Is it overheating? So I ask questions, right, to the agent. So my question was a natural language, right? I say, okay, this is the asset I'm monitoring, but I can't go inside it and see what is happening, right? So maybe from outside, I'm kind of, saying is that, is this asset is overheating? And if it is, maybe call someone, right? Like service request. So this is basically the natural language interaction, right? That we put it, right? And now you will see, right, these questions actually go to the agent and agent start thinking what I need to do, right? So the first step you can see, right, they will do a lot of steps, step 1, 2, 3, 4, 5. So I will not able to go in all the detail, but you will see they will do, it's a multi-step process. Just like you write an algorithm, you say, okay, my step 1 is this, step 2 is this. You see what happened is the step number 1, he started thinking, okay, this is the, okay, so literally, given these questions, agent started thinking is it actually overheating is somewhat related with that particular asset or not, right? Typically, it's like a cross check. You cross check it, right? So basically, these agents I was kind of, mentioning, right? They actually do 3 things one after another. So they will first say, okay, let me think. So this part is they are thinking, right? So LLM is thinking, saying is that, okay, I need to first check whether the chiller 11's, compressor can experience even an overheating or not, right? So this is a condition, right, that normally happen or not. So now what they do, they actually, because I wanted to do any check. So the second thing they will say, they will act on it. So act, it means they may call some remote call, right? So now they are calling some remote API, so that let me call that API and, get the information. So you can assume that I'm calling a remote API like a get failure mode information, and I'm saying chiller 11 is my input parameter, right? And that remote API is giving you information back. So this is the information they actually return to you. Saying is that, these are all the list of the failure mode that your asset can have. So this was one loop you can think like, right? Think, act, and observe. So this is basically a one loop that agent actually did, an LLM actually did, where it actually made an API call and then get the information. And agents are smart enough to read these things, and they might identify that overheating is appearing into the output. So I will go to the second step. So now they actually enter into the second step, right? And this second step say, okay, now I understand that, overheating is a kind of thing. I need to go and get, do I have a sensor data or not? So now they actually say, okay, let's go and get a sensor data, right? So they actually call another tool, okay, sensor data tool. And this time they don't actually download the data. They actually download a metadata. And the metadata, they also return the metadata. And you will see that they might be reading it here somewhere. The temperature should be there because they are smart enough to actually connect overheating with the temperature. You really don't need to write a program to do that. That's where I'm coming from, right? The way you write a program is completely changing. So now I think they have some understanding that temperature and overheating are somewhat related. Then they will process to say, okay, now I will try to do the anomaly detection, right? So you can see, right, like the way you build the anomaly models are kind of shifting, right? And then I'm not going into more detail, but I think over a process, you will see they start, they say, okay, I will build the anomaly detection model for the compressor overheating, right? And now they are using one of our foundation model on a time series like, TTM, which is very popular in Hugging Face from the IBM. So they are going to the Hugging Face, downloading that time series model, which is already pre-trained. It's pre-trained on the general data set, but these guys actually need pre-train on the chiller data. So actually it goes into the loop, saying I should actually fine-tune the model. So the process that you see, right? All these automation, get the data, fine-tune the model. If the anomaly happens, so we now detected the anomaly. It goes to the next step saying that I detected the anomaly, so I would like to actually make a service request, right? So they are actually making a service request, but now they are also cross-verifying. Maybe somebody else has already made a service request and I will not overflow it, right? So they are now also smart enough to actually say that somebody else has not done the, duplicate, right? Like, because multiple people might put a service request so that overeating is happening. So you see, this is basically the, innovation that are happening, right? Just in a one, this entire interaction, if you carefully see, how many problems did you solve in a one go, right? You solve the sensor disambiguation problem. You solve the fine tuning, problem. Then you also did a duplicate detection problem. And this is where, the agents are kind of, started kind of working. So these are all the examples that I think I had to kind of share with the team, but yeah, this is all basically the presentation from my side. So we can now go to the fourth presentation. It's about ontology, right? Thank you.
So on to the last session, the development and usage of dynamic process ontology. And what is this dynamic process ontology? What is the dynamic aspect of it? What is the process aspect of it? Why did we develop this ontology? Let's go into details of those. The dynamic and the process aspect will become more evident as we go over the contents that we have here. So we talked about how to So we talked about detecting anomalies and how do we, what are the challenges in detecting anomalies? And we saw that there are several neural network based models that can mine the pattern to detect the anomaly. But what can we do after? So in order to gain more information about this anomalies, so for example, which sensor is responsible for the anomaly? Should we stop this assembly process or can we plan our next steps so that the system can proceed with the assembly process? So how do we detect those? How can we get those information about what are the sensors which is responsible for the anomaly, which robot is responsible, to which robot the sensor is attached to, and so on. Just to recap, the assembly system that we are talking about consists of 4 robots assembling a toy rocket body part that is going on in a circle. So we have 4 robots and there are multiple sensors involved in this assembly process. But the sensors of interest to us are 2 sensors that are attached to 4 of these robots, which are called load cell and potentiometer. Now, before going into the details of the anomaly, let's just directly dive into how this ontology looks like. So this is the ontology that we have developed for the Future Factories manufacturing cell that we have. Let me try to get a little bit of a structure here. Okay, there we go. So you can see that this is slightly unconventional kind of an ontology. Generally, the ontologies that we have seen before consist of a list of sensors, list of robots that are present in a particular assembly setting, and how do they talk to each other. Here is where the process aspect comes in. So this particular ontology captures the entire assembly process of the manufacturing system itself. So the manufacturing system that we have, the assembly cell that we have, it's divided into 21 cycle states, where each cycle state can range from timestamp T1 to timestamp Tn. And the distance between the 1 and n can vary based on each cycle state. So looking at an abstractive level, what we can think of is in each cycle state, each robot is performing some action in the assembly process. So let's quickly see, yeah, that's the start. So let's quickly see how the information is stored in this particular ontology. So we have in total 21 cycle states that are involved in the assembly process. So here, basically, the robot 1 picks the tray from material handling station, and in cycle state 2, the robot 1 places the tray on the conveyor, and so on. So here, in this particular cycle state, we have robot 1, which is active. It has a gripper, and it has 2 sensors named potentiometers, and those are the item specifications and the functions of the sensor. And these are the item specifications and functions of a load cell. And this is the exact name of the variable using which this particular sensor value is being captured. And similarly, we have the same for the potentiometer here as well. And you can see that what is the expected value of this particular sensor is supposed to be during this timestamp is captured by this particular ontology. And it can also be noted that this ontology also captures which sensor becomes active in which timestamp and what is the expected range of that particular sensor in a given timestamp. So for example, here, we have potentiometer 1 from robot 1 having an is supposed to have values between 4,500 to 12,000. So while this happens, there is a sensor which is attached to robot 3, which might still be throwing anomalous values. But in this particular state, it's not supposed to be active. So that is totally fine. And these information is captured by this ontology. And this particular link is available in the notebook, so anyone can go ahead and play it. Similarly, we have cycle states going from 1 until 21, which finishes the final assembly process where robot 4 goes back to the home position. So that completes the assembly process. So now going through the notebook, given that initially what we did was we developed this ontology through several interactions with the domain experts. We used a tool called arrows.app, which lets us, let's see if I can open it. So which lets us interactively go ahead and develop this ontology, which we can later on load it to. So you can interactively go ahead and introduce nodes, add properties to these nodes, and etc. So this is very helpful when we are working with non-domain experts. We developed the ontology this way and then loaded this to Neo4j. But since we cannot get the Neo4j up here, we are going to go ahead and load the graph using network X, and then show how we can apply this ontology for the explainability of the anomaly that can potentially happen. So here we have the graph stored in a JSON file, and we went ahead and loaded the graph here. So the loaded graph looks as here follows. So this is the sample from the Neo4j that we originally had. So cycle state 4 has robot 2, has a gripper, load cell, potentiometer, and the corresponding values. So this is a test function that we wrote to make sure that the graph is loaded in the expected format, because we were porting from different formats of the graph from Neo4j to network X and Python and etc. So let's directly jump into how are we planning to go ahead and use this particular data set to generate the explanation. So here is a sample file given to us by the domain experts. So what happens here is, for a given row of information, so a row with the list of sensor values is given to a model, and any model which has predicted the anomaly to be no nose and no body 2, which means that the nose part of the rocket is missing and the body part 2 of the rocket is missing. And that's why the assembly process could not continue further. And during these respective timestamps, these are the values that we got from the sensors. So this particular classification model is deployed at the assembly cell site, which gathers the sensor data during the assembly process and dynamically classifies whether an anomaly has happened or not. So given that a row of information, an anomaly has happened, a model predicts an anomaly has happened, this particular row of information with the list of sensors can be passed on to the reasoner that we have built. So this anomaly reasoner takes in the input that is given by the model or given to the model, and also has the access to the ontology to see what is going on. And let's quickly look at the sample a sample explanation that is generated. So the sensor value that is given by the model in this particular timestamp is from potentiometer 2, the value is 2058. And that belongs to the cycle state 6. And the explanation in this particular example is generated for cycle state 6 to the potentiometer that we have here. And in this particular cycle state, the function of the robot is supposed to be robot 2 picks up the body part 2 from the conveyor. And in this particular cycle state, in this particular timestamp, the model has produced an anomalous value, 2058. And now why is that anomalous? Because in this particular cycle state, the value of the sensor is supposed to be somewhere between 6,000 to 12,000. And the function of the robot is picking up body part 2 from the conveyor, and the potential or possible anomalies that can happen is no body part 1 and no body part 2, and also no nose cone. And this is how we can generate explanation for each of the sections that we have here, each of the sensor data and the corresponding anomaly that has happened. And similarly, this can very well extend to the multimodal domain as well. So if an anomaly is being predicted or detected using an image data, we do have the corresponding sensor values there as well. So those corresponding sensor values can be passed on to the reasoner which has access to the ontology can generate these kind of explanations. And similarly, this extends to not just classification detection, also prediction models. So given timestamp 1 to timestamp n, we try to predict the values for timestamp n+1 to see if an anomaly is going to happen. In these cases too, if a model says an anomaly is going to happen, those sensor values can be passed on to the reasoner, which can reason about why these sensor values are anomalous, to which sensor this particular, to which robot the sensor is attached to, what is the function of that robot in that particular timestamp, and so on. So this can help us plan our next steps to see whether we should stop this assembly process or can we allocate the task to another robot to continue the process and so on. So the possibilities of what we want to do after is up to the domain and the assembly set that we have. And yeah, that concludes the development and the use of dynamic process ontology. The dynamic part here is, so each experiment setup can have different different values of the sensors. So for example, if we calibrate our equipment, the minimum and the maximum expected values in a given cycle state can differ. So these values can be dynamically updated to the ontology without having to change the entire schema of the ontology that we have built, since it exists in a label property graph format. So we can dynamically change the values without changing the entire schema. So that's where the dynamic part. The process part is, unlike the conventional ontologies, the process captures the entire assembly process itself. And hence the dynamic process ontology for user level explanation. And the notebook and the notebook and the GitHub repositories are available in the respective QR codes that we have provided here. And before the concluding remarks, any questions that we can address? Yes.
It's regarding the entire.
Oh, yeah. Go ahead.
Yeah, so I had a question regarding the usage of LLMs as a decision maker on different processes. So, sorry. Yeah, so my main question is regarding the example that Dr. Showed during the presentation. So, so regarding the entire process that was followed, did you have to create all of the different loops and the different decisions that the LLM should have to take? So, for example, first figure out where the overheating is happening, and then based on some specific rules that you previously decided, was it making these decisions as to what is the next step in its analysis, or was it all done by itself?
I mean, it's a part of the automation, so it should actually done by LLM.
Okay, then a follow-up regarding that. How do you then verify or confirm the accuracy of the process that is following?
So I mean, this is where the active area of research, you kind of do a lot of benchmark, just like we do benchmark on datasets. You also do the benchmark on the agent, right? Saying is that are they doing the expected tasks they are supposed to do or they are not. So basically, like it's in a very active area of research. I mean, this is the early stage. So yeah, I think there are a lot of benchmark needs to be done on a specific use cases. So that's the style that we actually all follow.
Yes, sir. All right. And regarding the example itself, is that an algorithm, or did you generate that?
Work kind of, as long as you learn how to prompt the LLM,
Yeah.
create proper system prompts, I think they should have.
Yes, sir. All right. Thank you. That's all.
Any further questions? I think that concludes the section. Thank you. Thank you all for taking your time to come and attend our session. Thank you.